Welcome to our comprehensive CCNA training session, where we will cover the 25 most important and highest-weighted concepts essential for the CCNA certification. This course is designed to equip you with the fundamental knowledge and skills required to effectively manage and operate network infrastructures. Whether you are preparing for the CCNA certification or aiming to enhance your networking expertise, this session will ensure a thorough understanding of both theoretical and practical aspects of networking. Before beginning, don't forget to like, share, subscribe, and hit the notification bell if you enjoy our content and find it helpful. By mastering these 25 critical concepts, you can expect to cover approximately 60 to 70% of the questions on the CCNA exam, as these topics are central to the certification. In this session, we will explore the 25 key CCNA concepts starting with IP addressing, focusing on IPv4 subnetting, VLSM, and IPv6 basics to manage and optimize IP address allocations. We will delve into routing concepts and protocols, including static routing, OSPF, and EIGRP, to ensure optimal path selection and network efficiency. Layer 2 technologies like Spanning Tree Protocol, STP, and EtherChannel will be explored for managing switching environments and preventing loops. Understanding VLANs and Inter-VLAN routing is crucial for network segmentation and communication. We will discuss network services such as DHCP operations for dynamic IP allocation and NAT types for managing public and private IP addressing. Network security will be emphasized through access control lists, ACLs, port security, and VPN technologies to protect network integrity and data transmission. Advanced technologies and services, including software-defined networking (SDN), network automation, and quality of service (QoS), will be covered to optimize performance and streamline management tasks. Network management and troubleshooting will be addressed through SNMP for monitoring, syslog for event logging, and key diagnostic commands for resolving issues. Finally, we will review network design and implementation principles, including hierarchical design, spine-leaf architecture, and SD-WAN, to build scalable, efficient, and robust networks. This comprehensive agenda ensures a solid foundation in network engineering, preparing you for the dynamic needs of modern enterprises. By mastering these 25 critical concepts, you will be well equipped to design, implement, and manage resilient and efficient networks, meeting the ever-evolving demands of today's networking environments. Understanding IPv4 addressing is foundational for network design and management. IPv4 addresses are 32-bit numeric labels divided into 4 octets, each ranging from 0 to 255, used to identify devices on a network. Subnetting divides a network into smaller subnetworks, enhancing routing efficiency and security. A subnet mask distinguishes the network portion from the host portion of an IP address. For example, in a subnet mask of 255.255.255.0, the first 3 octets, 24 bits, represent the network portion, while the last octet, 8 bits, represents the host portion. VLSM, variable length subnet masking, allows subnets to be further divided into smaller subnets, optimizing IP address usage and accommodating networks of varying sizes without wasting addresses. Route summarization aggregates multiple subnets into a single route, reducing the size of routing tables and simplifying network management. Summarization is typically performed at classful network boundaries like /8, /16, or /24, making it easier to manage large networks. Mastering IPv4 addressing, subnetting, VLSM, and summarization is crucial for efficient IP address management and network design, forming the backbone of network engineering and troubleshooting. In practice, effective IPv4 management ensures robust, scalable, and secure network operations, addressing the dynamic needs of modern enterprise environments. IPv6 addressing resolves the limitations of IPv4, offering a vastly larger address space and improved network functionality. IPv6 addresses are 128-bit identifiers that provide ample addresses for the foreseeable future, accommodating the growing number of Internet-connected devices. There are several types of IPv6 addresses. Global unicast addresses are public and globally routable, similar to IPv4 public addresses. Link local addresses are automatically configured for local communication within a single link and are essential for basic network operations. Unique local addresses are private, akin to IPv4 RFC 1918 addresses, used within a site or organization for internal communications. UI64 facilitates automatic host address configuration from the MAC address, ensuring unique addresses within a network by inserting FFFE in the middle of the MAC address and inverting the 7th bit. Neighbor Discovery Protocol, NDP, replaces ARP and IPv6, discovering link layer addresses and routers on the same network. It also handles address auto-configuration, duplicate address detection, and redirection, enhancing network reliability and efficiency. IPv6 addressing, with its larger address space and enhanced features like UI64 and NDP, is critical for modern network design, enabling seamless and scalable internet connectivity. Embracing IPv6 is essential for future-proofing network infrastructure and supporting the continued expansion of the internet. Static routing involves manually configuring routes in a router's routing table, essential for simple, stable networks or as backup routes in more complex setups. Static routes are configured using the IP route network, mask, next hop address command, directing packets to the specified network via a predetermined path. Default routes match any destination not explicitly listed in the routing table, serving as a catch-all route. In IPv4, the default route is 0.0.0.0/0, while in IPv6 it is :/0. Floating static routes act as backup routes with a higher administrative distance than primary routes, only taking over if the primary route fails, ensuring network resilience. Static routing, with its straightforward configuration and predictable behavior, is a fundamental skill for network administrators, ensuring reliable and controllable packet forwarding. It is particularly useful in small or static networks where route changes are infrequent. Mastery of static routing is critical for troubleshooting and designing resilient network infrastructures. Understanding the nuances of static routes, default routes, and floating static routes equips network professionals with the tools to create stable and efficient network architectures. Dynamic routing protocols automatically adjust routes based on network topology changes, ensuring efficient and resilient data delivery. Administrative distance (AD) measures the trustworthiness of a routing source, with lower AD values being preferred, guiding routers to select the most reliable path. Metrics determine the best path to a destination, considering factors like hop count, bandwidth, delay, reliability, and load, helping balance network traffic and optimize performance. Convergence is the time it takes for all routers in a network to update their routing tables after a change. Faster convergence improves network stability and reduces downtime. Understanding dynamic routing protocols, including their administrative distance, metrics, and convergence, is crucial for maintaining an adaptive and efficient network. Protocols like RIP, OSPF, EIGRP, and BGP each have unique characteristics and uses, with OSPF and EIGRP being commonly used within autonomous systems, while BGP is essential for inter-autonomous system routing on the Internet. Mastery of dynamic routing protocols is essential for network engineers to design scalable, responsive, and robust networks capable of adapting to changing conditions and maintaining optimal performance. OSPF is a robust link-state routing protocol widely used in large enterprise networks for its scalability and rapid convergence. OSPF routers share information using link-state advertisements, LSAs, detailing the state of each link. There are different types of LSAs, type 1 to 5, that communicate various aspects of the network topology. OSPF divides networks into areas to optimize routing: backbone, area 0, normal, stub, totally stubby, and not so stubby area, NSSA. OSPF establishes neighbor relationships through states: down, attempt, init, two-way, xstart, exchange, loading, and full, representing the progression of neighbor establishment and synchronization. Router roles include designated router (DR), managing LSA distribution on multi-access networks, backup DR (BDR), assuming the DR role if the current DR fails, and DR other, regular routers that are neither DR nor BDR. OSPF uses the Dijkstra's shortest path first (SPF) algorithm to compute the most efficient route, ensuring optimal data delivery. Mastering OSPF, including LSAs, router roles, neighbor states, area types, and path selection, is essential for managing complex and large-scale networks effectively. Its hierarchical design and efficient use of resources make OSPF a cornerstone for enterprise-level routing, ensuring high availability and optimal network performance. EIGRP is an advanced distance vector routing protocol, offering rapid convergence and efficient network operation. EIGRP uses the diffusing update algorithm dual to ensure loop-free and efficient route computation, maintaining a topology table with all learned routes and managing them through route states. Routes in EIGRP can be in either an active state, where no feasible successor exists, or a passive state, where a successor route is available. The protocol distinguishes between successors, the primary route with the lowest cost to a destination, and feasible successors, backup routes that meet the feasibility condition where the reported distance, RD, is less than the feasible distance, FD. EIGRP uses composite metrics based on bandwidth, delay, load, and reliability to select optimal routes, providing flexibility and efficiency in routing decisions. Understanding EIGRP, including its dual mechanism, topology table, route states, successors, and feasible successors, is crucial for ensuring efficient and reliable network routing. EIGRP's capabilities make it suitable for a variety of network environments, from small offices to large enterprise networks, where it provides fast convergence, scalability, and robust routing capabilities. STP is essential for preventing switching loops in redundant topologies, ensuring network stability and preventing broadcast storms. The original STP standard, 802.1d, provides a loop-free topology by disabling redundant paths until needed. RSTP, Rapid Spanning Tree Protocol, improves convergence time significantly, making it suitable for modern networks. PVST+, per VLAN Spanning Tree Plus, allows for a separate STP instance for each VLAN, optimizing load balancing and redundancy. PortFast enables faster network connectivity on access ports by skipping the learning and listening states, while BPDU guard enhances security by disabling a port if it receives a BPDU, preventing potential loops caused by misconfigured devices. Understanding STP, including its various enhancements like RSTP and PVST+, along with features like PortFast and BPDU guard, is crucial for maintaining stable and efficient switch networks. Mastery of STP ensures that network engineers can design robust networks that maximize redundancy, while avoiding the detrimental effects of switching loops. EtherChannel combines multiple physical links into one logical link, enhancing bandwidth and providing redundancy. LACP, Link Aggregation Control Protocol, is an open standard protocol used to manage EtherChannel, while PAGP, Port Aggregation Protocol, is Cisco's proprietary protocol. EtherChannel can operate at Layer 2, switching, or Layer 3 routing, providing flexibility in network design. Load balancing in EtherChannel is based on source/destination MAC or IP addresses and port numbers, optimizing traffic distribution across the links. Understanding EtherChannel, including its protocols like LACP and PAGP, and its load balancing mechanisms, is essential for improving network performance and redundancy. Implementing EtherChannel effectively can significantly enhance network throughput and fault tolerance, making it a valuable tool in the design of high-performance, resilient network infrastructures. VLANs logically segment a switch into separate broadcast domains, improving network management and security. Access ports belong to a single VLAN, while trunk ports carry traffic for multiple VLANs using the 802.1q trunking protocol, which tags frames with VLAN IDs. The native VLAN handles untagged traffic on a trunk, with VLAN 1 being the default. DTP, Dynamic Trunking Protocol, negotiates trunking between switches, simplifying VLAN management. Understanding VLANs, including access and trunk ports, 802.1q tagging, native VLANs, and DTP, is crucial for optimizing network segmentation and enhancing security. VLANs enable network administrators to isolate traffic, reduce broadcast domains, and improve overall network performance and security. Effective VLAN implementation is key to managing large, complex networks and maintaining efficient, secure communication channels. Inter-VLAN routing allows communication between VLANs, essential for network functionality. A common method is router on a stick, where a router with subinterfaces for each VLAN routes traffic between them. Switch virtual interfaces (SVIs) provide VLAN interfaces for routing on Layer 3 switches, enabling inter-VLAN routing without additional hardware. Layer 3 switches can route between VLANs using dedicated routing capabilities. Understanding inter-VLAN routing, including router on a stick, SVIs, and Layer 3 switching, is essential for enabling efficient communication across segmented networks. Effective inter-VLAN routing ensures seamless connectivity within an organization, allowing different departments or user groups to communicate securely and efficiently, while maintaining network segmentation for security and performance. DHCP automates the assignment of IP addresses, subnet masks, gateways, and DNS information to network hosts, simplifying network administration. A DHCP server leases IP addresses to clients, while a DHCP relay forwards requests to servers on different subnets. DHCP snooping prevents unauthorized servers from assigning IP addresses, enhancing security. DHCP options provide additional configuration parameters, such as option 150 for specifying TFTP servers. Understanding DHCP, including its server and relay functions, security features like snooping and various options, is crucial for efficient and secure IP address management. Implementing DHCP effectively reduces administrative overhead, ensures consistent IP address assignment, and enhances network security by preventing unauthorized devices from receiving network configurations. NAT translates private IP addresses to public IP addresses, facilitating Internet access and conserving public IPs. Static NAT provides a one-to-one mapping, while dynamic NAT uses a pool of public IPs for many-to-many translations. PAT, port address translation, allows many private IP addresses to share a single public IP, differentiating sessions by port numbers. NAT distinguishes between the inside private network and outside public network. Understanding NAT, including static NAT, dynamic NAT, PAT, and the concepts of inside and outside networks, is essential for managing IP address translation and enabling secure Internet connectivity. Proper NAT implementation is critical for extending the lifespan of the IPv4 address space, enabling private networks to access external resources while maintaining security and privacy. ACLs filter network traffic by specifying which packets are allowed or denied based on criteria such as source/destination IP, protocol, and port. Standard ACLs filter traffic based on source IP addresses, while extended ACLs provide more granular control by filtering on source and destination IPs, protocols, and ports. Named ACLs use descriptive names instead of numbers, and time-based ACLs are active only during specified times. Understanding ACLs, including standard, extended, named, and time-based ACLs, is crucial for implementing effective network security policies. ACLs are fundamental tools for controlling traffic flow, preventing unauthorized access, and protecting network resources from potential threats. Properly configured ACLs enhance security, ensure compliance with network policies, and help maintain a secure and efficient network environment. Port security limits the MAC addresses allowed on a switch port, preventing unauthorized access and enhancing network security. Violation actions include protect, drops unauthorized frames, restrict, drops unauthorized frames and generates a log, and shutdown disables the port. MAC address types include static, manually configured, dynamic learned and forgotten after reboot, and sticky learned and saved to the configuration. Understanding port security, including its violation actions and MAC address types, is essential for securing switch ports and preventing unauthorized network access. Implementing port security measures helps mitigate risks associated with unauthorized devices, enhances overall network security, and ensures that only trusted devices can connect to the network infrastructure. VPNs securely connect sites or users over an untrusted network, ensuring data privacy and integrity. Site-to-site VPNs connect entire networks using IPsec, while remote access VPNs connect individual hosts to a network, with options for client-based, requiring VPN client software, and clientless, using SSL and a web browser connections. IPsec protocols include authentication header, AH, and encapsulating security payload, ESP, with Internet Key Exchange, IKE, managing the security associations. Understanding VPNs, including site-to-site and remote access types, IPsec protocols and client options, is crucial for implementing secure network connections. VPNs play a vital role in protecting data transmitted over the Internet, ensuring secure communication for remote workers, and connecting branch offices securely to the corporate network. Proper VPN implementation enhances security, privacy, and access control for sensitive information and resources. Network automation streamlines configuration and management using tools like REST APIs, which utilize HTTP methods, GET, POST, PUT, DELETE, and data formats, JSON, YAML. Software-defined networking, SDN, separates the control and data planes, allowing centralized network management. Cisco DNA Center provides centralized management for SD access. Understanding network automation, including REST APIs, data formats, SDN, and tools like Cisco DNA Center, is essential for efficient and scalable network operations. Automation reduces manual intervention, minimizes errors, and accelerates the deployment of network services. Embracing network automation enables network administrators to focus on strategic tasks, enhances operational efficiency, and supports the dynamic needs of modern enterprises. Configuration management automates the deployment and maintenance of network configurations. Tools like Puppet, desired state configuration, Chef, recipes describing configurations, and Ansible, YAML playbooks, agentless via SSH, are widely used. Cisco VIRL, Virtual Internet Routing Lab, allows virtual network simulations for testing and training. Understanding configuration management, including tools like Puppet, Chef, Ansible, and Cisco VIRL, is crucial for automating network operations and ensuring consistent configurations. Effective configuration management improves network reliability, accelerates deployment, and simplifies the management of complex network environments. Automating configuration tasks ensures that network devices are consistently configured according to best practices, reducing the risk of configuration errors and enhancing overall network stability. Wireless LANs use various 802.11 standards, A, B, G, N, AC, and AX, for wireless communication, with security protocols like WPA2, using AES encryption and 802.1x/EAP authentication, and WPA3, using SAE. WLAN controllers provide centralized management of access points, APs, enhancing network scalability and security. Understanding LANs, including 802.11 standards, security protocols, and WLAN controllers, is essential for deploying and managing wireless networks effectively. Implementing robust security measures ensures that wireless networks are protected against unauthorized access and potential attacks. Proper WLAN management enhances user mobility, ensures reliable connectivity, and supports the increasing demand for wireless communication in modern enterprise environments. QoS manages network congestion and prioritizes traffic to ensure reliable performance for critical applications. QoS models include best effort, IntServe using RSVP, and DiffServe using DSCP. QoS tools include classification and marking, COS, IP precedence, DSCP, queuing, priority queuing, CBWFQ, congestion avoidance, WRED, and traffic shaping and policing, CAR, class-based policing. Understanding QoS, including its models and tools, is crucial for optimizing network performance and ensuring the quality of service for various applications. Implementing QoS policies ensures that high-priority traffic, such as voice and video, receives the necessary bandwidth and low latency for optimal performance. QoS enhances user experience, supports service-level agreements, SLAs, and maintains network efficiency even under heavy traffic conditions. IP services provide essential network functionalities, including SNMP, Simple Network Management Protocol, for network management, syslog for system message logging, NetFlow for IP traffic information collection, NTP, Network Time Protocol, for time synchronization, and FTP/TFTP for file transfers. Understanding IP services, including their functionalities and configurations, is crucial for maintaining and managing network operations efficiently. Implementing IP services ensures that network administrators can monitor, analyze, and maintain network health, troubleshoot issues effectively, and synchronize network devices accurately. Proper management of IP services enhances overall network visibility, reliability, and operational efficiency. Infrastructure security encompasses AAA, authentication, authorization, accounting protocols like Radius and TCAX+, providing centralized user authentication and access control. 802.1x port-based authentication secures network access using EAP types, PAP, APTLS, and MACSEC provides Layer 2 encryption between switches. Understanding infrastructure security, including AAA protocols, 802.1x authentication, and MACSEC, is essential for protecting network resources and ensuring secure access. Implementing robust security measures protects against unauthorized access, data breaches, and network threats. Comprehensive infrastructure security policies enhance the protection of sensitive information, ensure compliance with security standards, and maintain the integrity and availability of network services. FHRPs provide redundancy for the default gateway, ensuring network availability. HSRP, Hot Standby Router Protocol, and VRRP, Virtual Router Redundancy Protocol, offer active/standby configurations, while GLBP, Gateway Load Balancing Protocol, provides load balancing with an active virtual gateway, AVG, and multiple active virtual forwarders, AVF. Preemption allows a higher priority router to take over as active/master, and object tracking adjusts priorities based on tracked objects. Understanding FHRPs, including HSRP, VRRP, GLBP, preemption, and object tracking, is crucial for ensuring network reliability and redundancy. Implementing FHRPs ensures that networks remain available even during hardware failures or maintenance, providing seamless failover and load balancing capabilities. Proper configuration of FHRPs enhances network resilience, minimizes downtime, and ensures continuous access to critical network resources. Infrastructure maintenance involves tasks like password recovery, interrupting boot and changing the config register, iOS upgrades, using TFTP/FTP servers and copying to flash, and licensing management, right to use, product activation key, smart licensing. Understanding infrastructure maintenance, including password recovery, iOS upgrades, and licensing, is essential for keeping network devices updated and operational. Regular maintenance ensures that network devices run the latest software versions, addressing vulnerabilities and improving performance. Proper licensing management ensures compliance with software agreements and access to necessary features. Effective infrastructure maintenance practices enhance network reliability, security, and overall performance. Network troubleshooting requires a structured approach to identify and resolve issues efficiently. The OSI model, Physical Data Link, Network Transport Application, guides troubleshooting steps. Key commands include ping and traceroute for connectivity testing, and show commands show IP-int brief, show IP route, show run, show version, for examining configurations and status. Understanding network troubleshooting methodologies, including the OSI model and key commands, is crucial for diagnosing and resolving network issues effectively. A systematic troubleshooting approach helps pinpoint problems quickly, reduces downtime, and restores network services efficiently. Mastery of troubleshooting techniques and tools ensures that network administrators can maintain network stability, performance, and availability. Network design methodologies include the three-tier hierarchical model, core, distribution, access, providing scalability and redundancy. The spine leaf class architecture offers high bandwidth connectivity between core, spine, and access leaf layers. Software-defined networking (SDN) separates control and data planes, enabling centralized control. SD-WAN software-defined WAN uses centralized management for network overlays, optimizing WAN performance. Understanding network design methodologies, including the three-tier hierarchical model spine leaf architecture, SDN and SD-WAN, is essential for creating scalable, efficient, and robust networks. Effective network design ensures optimal performance, flexibility, and scalability, meeting the dynamic needs of modern enterprises. Properly designed network architectures support high availability, simplify management, and enhance overall network performance and reliability. As we conclude our review of essential CCNA concepts, it's crucial to integrate these key takeaways into your study and practice routines. First, master IP addressing by focusing on IPv4 subnetting, VLSM, and IPv6 basics, ensuring you can effectively manage and optimize IP address allocations. Understanding routing protocols such as OSPF, EIGRP, and static routing is fundamental for optimal path selection and maintaining network efficiency. Layer 2 technologies, including spanning tree protocol, STP, EtherChannel, and VLANs, are vital for managing switching environments, preventing loops, and segmenting networks logically. Network services such as DHCP operations for dynamic IP allocation and various NAT types for public and private IP addressing are essential for efficient network operations. Implement robust network security measures with access control lists, ACLs, port security, and VPN technologies to protect network integrity and secure data transmission. Embrace advanced concepts like software-defined networking (SDN), network automation, and quality of service (QoS) to optimize performance and streamline management tasks. Efficient network management requires proficiency in SNMP for monitoring, syslog for logging events, and effective iOS management to maintain network health. Understanding and implementing redundancy protocols like HSRP, VRRP, and GLBP is crucial to ensure network availability and minimize downtime. Master troubleshooting methodologies and key diagnostic commands to quickly identify and resolve network issues, maintaining network reliability. Finally, apply network design principles such as hierarchical design, spine leaf architecture, and SD-WAN to build scalable, efficient, and robust networks. By comprehensively understanding and integrating these concepts, you will be well equipped to design, implement, and manage resilient and efficient networks, meeting the dynamic needs of modern enterprises. Continue to practice, explore, and stay updated with the latest networking trends to excel in your CCNA certification and beyond.